Hey guys, welcome back. Today we are going to be learning how to use those units that we learned about in our last class. Now, the thing that we want to make sure we're doing is that when we use units in equations, that our equations themselves, they must be what we call dimensionally consistent. Okay, now what does this mean? When we measure things or talk about quantities, we can discuss different types of dimensions. And these are things like length or mass or time. Or we could talk about other dimensions, dimensions of happiness or money or apples or whatever. But we want to make sure that when we have two sides on an equation, both sides are using the same dimension, right? So for example, if I have an equation where one side is talking about time and the other side is talking about mass, well, that just doesn't work, does it, right? You can't have 5 seconds somehow equal to some number of kilograms. The wrong dimension, okay? So equations must be dimensionally consistent. And the easiest way that we do this is to ensure that they have the same units. That's how we're going to be able to check this, okay? So let's do a quick example here to illustrate. Let me give you some information. I'm going to tell you that the density of water is 1,000 kilograms per cubic meter, which is it's pretty heavy stuff. And I'm also going to tell you that I've got half a cubic meter of water right here, okay? And I want to know what is the mass of this water. Okay, now this is not a difficult question to do, but we're going to step through it. And what we'll do is we'll try to recall the IC sort of a stepwise procedure that we learned in last lesson. This stands for identify, set up, execute, and evaluate. Okay, it's a way of solving physics problems. So identify what we know, what we need to know, right? Well, we just did that right now. Okay, so we want to know what is the mass of water, and we do know the density of water, and we do know the volume of water that we have. So now when we set this up, we're going to try to figure out what kind of equation we want to use. Well, we know that density is equal to mass over volume, right? So we can rearrange this to solve for mass, which is what we want to know, where mass is equal to density times volume. So let's run with that and set up this equation, okay? We're going to say that the mass of the water is equal to the density of the water, which is 1,000 kilograms per meter cubed, multiplied by the volume of water, which is 0.5 meters cubed. And we can just execute and solve this right now. And we can see this 1,000 times 0.5 is 500. And the units is going to be, well, you see the meters cubed cancel. So we're left with kilograms. That's going to be our answer. And let's evaluate it. Just check to see if it makes sense. Does 500 kilograms make sense? Yeah, I mean, the density is 1,000, and we have per cubic meter, we have less than 1 cubic meter, so it should be less than 1,000. 500 is less than 1,000. That's good. And as far as the units go, we got kilograms, which is what we're looking for mass. And on the left side of the equation, the meters cubed cancel, so we're left with kilograms. And so we have a dimensionally consistent equation. And that's what we're checking for. That's a good check when we evaluate our answer. We want to make sure it's dimensionally consistent, okay? You could imagine it might be easy to make a mistake. Now, this example is pretty simple, but in more complicated equations, it can get easy to sort of slip up and invert something or make a mistake. So let's say we didn't write down the units and we had 1,000 divided by 0.5 is going to equal our answer. What's this? So we do the math. That's 2,000 kilograms. Okay. Now, at the evaluation step, this is when we sort of check ourselves. Now, we look at the magnitude. We say 2,000 kilograms. Well, that's more than 1,000. That doesn't really work very well. But if we miss that, we should at least be able to catch the units and make sure that these are dimensionally consistent. And that's where this also fails. Because we didn't write the units, we don't see it. But if we did write them down, we would. So let's write them down. This is kilograms per cubic meter, and this is cubic meters. We can rearrange this. We can actually try and solve what that is. Kilograms per cubic meter over meters cubed over 1. That's really what this is. And so now we know we have these two fractions. You can take the one in the denominator, bring it up and invert it and multiply them together. So we know that this is equivalent to kilograms over meters cubed times 1 over meters cubed, which is equal to kilograms per meters to the 6th power. And this is quite obviously garbage and not the same as kilograms. And these are not dimensionally consistent on both sides of the equation. And so this is wrong because we made a mistake. It's a good way to check that you're doing things right. That's why you always, always, always use units in your calculations, because they will tell you if you made a mistake. Okay, now is when things get a little bit more interesting. We're going to be talking about dimensional analysis. This is the useful part of using units, and it's actually about learning how to convert units. Let me give you a new conversion factor here. And it's a pretty simple one. I'm just going to tell you that 1 kilogram is equal to approximately 2.2 pounds. Okay, and what I want to do is I want to go back and grab this 500 kilograms of water, and I want to convert it into pounds. Okay, that's it. We're just going to convert kilograms to pounds. Not a big deal, okay? How do we do this? Well, the very first step we're going to do is we're going to multiply 500 kilograms by 1. Yes, by 1. What does that give us? 500 kilograms. We did it. You weren't expecting that, were you? Okay, so what did we do? Well, we multiplied by 1. You're thinking to yourself, that did nothing. Stop wasting my time. But I'm here to tell you, there is something very sneaky going on here. Multiplying by 1 turns out to be sort of this ninja move that we can use to convert any unit into our target unit. And we can do it again and again and again, and we will. Why do I want to say it this way? Because I want you to sort of understand that when you have 500 kilograms of water and you multiply it by 1, you still have that same quantity of water. What we're going to do is, instead of multiplying by the number 1, we're going to multiply by a value that is equivalent to 1. And by doing that, we will maintain the same quantity, but we will change the units. Let's see how this works. All right, so we're going to multiply by 1 again, but we're going to multiply instead of the number 1, it's going to be a value of 1 based on the conversion factor. Let's look at this conversion factor here. What would happen if I divided both sides of this equation by 2.2 pounds? I would get 1 kilogram divided by 2.2 pounds on the left side, and on the right side, the 2.2 divided by 2.2, that would just cancel out and give us 1, the magic 1, right? I could also conversely divide both sides of this equation by 1 kilogram, right? The left side would be 1 kilogram divided by 1 kilogram. Well, that's 1. And the right side would be 2.2 pounds divided by 1 kilogram. So here I have 3 different ways of writing down 1. And I'm going to choose one of them to multiply by 500 kilograms to convert our unit. All right, so let's do that. I'm going to choose the 2.2 pounds per 1 kilogram conversion factor here. Now this is equivalent to 1, so I'm not changing the quantity of 500 kilograms, but let's see what does happen. When I do this, I can do the math. 500 times 2.2, that should give us 1100. And for the units, we see that the kilograms cancel, and we're left only with pounds in the numerator. And there we go, 1100 pounds. That's our answer. The quantity of 1100 pounds and the quantity of 500 kilograms, they're the same because I just multiplied by 1, so the quantity didn't change. Just the units changed. The name that I used to measure how much there, that's what changed. Okay, why did I choose this conversion factor, right? I chose this one and not this one. Why? Well, what happens if I chose this first conversion factor? We would get 500 kilograms times 1 kilogram over 2.2 pounds, right? What would that give me? Well, that would give me, let's do the math, 500 over 2.2. 500 over 2.2, 227. Okay, 227. And if I look at the units don't really go anywhere, right? Nothing cancels. I wind up getting kilograms squared over pounds. This, my friends, makes me a little bit unhappy because this is kind of a useless result. These units, useless. The one on top, amazing. I'm happy to get this. I want to simply get pounds, kilograms to pounds. I don't want to convert kilograms into kilograms squared per pound, right? That doesn't get me anywhere. So although these two results are mathematically equivalent, they are not equally useful. And so for that reason, we're not going to do it this way, and we're going to make a rule. The rule is that when we multiply by 1, when we plug in that conversion factor, we're going to arrange it in a certain way. We want to arrange our conversion factor. So the so-called bad units will cancel, right? I want to get rid of kilograms. I want them to cancel. And so I'm going to choose the conversion factor in this case where kilograms is in the denominator, and then it will cancel with the 500 kilograms that's in the numerator. That's it, right? So just look at what you're looking for, your target, and arrange your conversion factor appropriately so that you can cancel out the bad units. Let's try one final example to drive this point home. And I will give you another new conversion factor. I'm going to tell you that there are 30 grains of rice in 1 teaspoon. All right, so you got a teaspoon, you can put grains of rice in it, you get up to 30, it's full. Okay, that's the conversion factor. I want you to tell me the answer to this question. Here's the question. How many teaspoons of rice are there per pound if there are 10,000 grains of rice per kilogram? Okay, that's kind of a confusing question, right? We have to sort things out so that we can solve it. Let's use that IC method again. We're going to identify what we know and what we need to know, okay? So what do we need to know? What's our target here? Well, we want to know teaspoons of rice per pound, right? This is sort of our target. What is this number? How many teaspoons of rice per pound? Okay, cool. What do we know? Well, we definitely know that there are 10,000 grains of rice per kilogram. We're given that information right here, right? And we also have a conversion factor. We know that there are 30 grains of rice per teaspoon, and we have another conversion factor from up here. We know that there is 1 kilogram for every 2.2 pounds. Okay, this is what we know. We've identified everything. Let's set up and execute this problem now. So we're going to start out with what the problem tells us is we have 10,000 grains of rice per kilogram. Okay, we're going to try and get rid of grains and replace them with teaspoons, and get rid of kilograms and replace them with pounds. Okay, so whichever one we want to do first is fine. Let's try and get rid of kilograms and replace them with pounds first. Okay, so we're going to multiply by 1. We're going to use a conversion factor here. We're going to use this one, right? Converting kilograms to pounds. We're going to multiply by 1 kilogram for every 2.2 pounds. And once we do that, the kilograms will cancel and we will have correctly gotten pounds in the denominator, which is what our target is. So that's good. We're halfway there. We're going to have an answer now in grains per pound. We want teaspoons per pound. So we need to convert away grains into teaspoons. Let's do that. Let's plug in this other conversion factor we have here, and that's 30 grains per teaspoon. Okay, perfect. And now that we have that in, we can see that we messed up, didn't we, right? Nothing cancels. We didn't arrange the conversion factor correctly. We want that grains to cancel. So let's invert it. Okay, let's invert this. And we're going to say there's 1 teaspoon for 30 grains of rice. And now I think we're done. We can now cancel out grains with grains, and we'll have teaspoons in the numerator, pounds in the denominator. We're good. Let's do the math. Okay, so we've got 10,000 times 1 divided by 2.2 divided by 30. That gives us about 150. Okay, 150, and the units are teaspoons per pound, right? No grains, no kilograms in the numerator, no kilograms, no grains in the denominator, only teaspoons and pounds survive. And now we've solved the problem. That's going to be our answer right there. 10,000 grains of rice per kilogram is the same as 150 teaspoons of rice per pound. Kind of useless, but it's an example here of how we can use dimensional analysis to convert pretty much any unit into any target unit. Just have to keep multiplying by 1 again and again and again until you get there, and you will. It's very powerful. So yeah, that's all we have for today. If you have any questions, leave them down in the comments. You can give me a thumbs up and a like if you think that this helped you out. And sub to get more content. The next lesson we'll be doing some exercises, so you can download a PDF of exercises from my website. And the link is in the description. You can then do those exercises before viewing the next class where we'll go over them and do them together for some extra practice. Okay, hope that's good, and I'll see you next time. Bye-bye.